Hi, how are you doing? I'm Mohammad Sadri, postdoctoral researcher at Electrical Engineering Department of TU Kaiserslautern, Germany. This is video section 5 of lesson 9, and lesson 9 was generally about, in fact, transferring data from an AXI stream interface to an AXI memory mapped interface. And as a kind of practical experiment, we selected the ZYNQ device and we transferred data from the AXI stream pipeline that we had on the ZYNQ PL to the DRAM memory on the ZYNQ PS. So this is something that I have already shown you in the previous, in fact, 4 videos of this lesson. And I have shown you practically how you program the AXI DMA module, which is actually one of the IP cores of the Xilinx. And I executed the program on the Z board and I showed you that it is working. So up to this point, I have just shown you that it is working, but I have not done any analysis on the performance speed of this guy and if this guy is always working correctly. So right now, in this specific video, what I want to do, I want to show you how you debug your software on the board using Xilinx SDK. So as you write your code inside Xilinx SDK, you want to run your code on your ZYNQ device and then on your ARM host on the ZYNQ device, and actually you want to be able to debug your code and in fact to single step through your code and to see different parameters, different values and different registers and overall the behavior of your code. So this is something we focus on in this video. And another interesting thing that I'm going to show you in this video is what happens when you update your design between different versions of Vivado. For example, you have created your design using Vivado 2014.1 and now you have installed a new version of Vivado, for example 2014.2, and what happens during this upgrade, how the upgrade will happen. Or for example, you have an IP, you have used an IP block from someone in your design and then he updates his code, and now how this IP update will happen. So this is another thing that I show you, but practically I show you the update thing in the first phase of the video and then the debugging in the second phase of the video. And yeah, the important point maybe I should mention is that during my test I found a bug actually in the sample generator module, and so the RTL of sample generator module is changed slightly, very slightly in comparison with what I did in lesson 7. Actually, it is working in lesson 7, but then in some special situations it has some problems. Now I think that the problem is fixed. And I will address this in the next video when I'm going to show you the performance of this module and the bandwidths that we can get from an AXI DMA module when we are transferring data from the ZYNQ PL to the ZYNQ PS. Okay. If you liked the videos, please make a donation, and using your donations I will buy new hardware and I will do more tests and I will create more videos useful for everybody. So let's get started. Okay, so I want to open the Vivado project that I have created before using Vivado for 2014.1, and I have upgraded the tool to 2014.2, and I go ahead, I open the project and let's see what happens. And this is kind of interesting, and this is something that you will definitely encounter during your work, because you design something with a previous version of Vivado and then you upgrade your Vivado to a new version, and then what will happen? Actually, when the project gets open, the tool will ask you this project is being created by a previous version of Vivado, should I update the project? And you will say yes. So it didn't ask me right now because I have done this step before. But now I have designed this block diagram using Vivado 2014.1, and I'm in fact now opening the same block diagram using 2014.2, and what is happening is that the design has 10 blocks that should be upgraded. In fact, there are 10 blocks here for which Vivado 2014.2 has a newer version than 2014.1. So I click on report IP status, and if I do so, in IP status tab down here, I will have in fact a list of the blocks that should be upgraded. Okay, and here you can select which of the IP components you want to upgrade and which you want to keep as it is, and here you see the current version that you have for the IP and in fact the recommended version, and here in the list also we see the sample generator actually, which is our own block, is not related to Vivado, and the reason is from the previous video that I recorded for you, and we tried the sample generator module and XRDMA, and I showed you this configuration is working. From that time I have made an update on sample generator, and I will talk what kind of update I have made. Here is actually very simple. I have just increased the frame size to 32 bits. So all of these IP blocks, they are all selected, and I come here, upgrade selected, and I press upgrade selected, and yeah, let's press OK. So it will begin upgrading your IP blocks, and I believe this is something necessary. Okay, I pause the video until it gets finished. Okay, now I have received this critical message which says in fact one of the external ports of this sample generator is changed, and this is actually true. In the sample generator I decided to increase the size of the frame size, in fact input, and if you remember, the frame size was indicating the length of the packet. I mean how many bits of data I transfer before I generate the TLAST signal. So the frame size was indicating the size of each frame or size of each packet that the sample generator is producing. So actually this is a correct warning, and I'm aware of this warning, so I just press OK, and now the report that I have here is out of date. So let's okay, now here I have in fact the updated report, and what do I see here? I see that now for all of my blocks no change is required, and they are now the latest version. And I think this is something that will definitely happen to you when you are working on different projects using the Vivado environment. Okay, now obviously synthesis and implementations are out of date, and I should run synthesis and implementation again. So the connections here, they are, let me check if the connections, they are all fine, and if they look fine, because now I want to run synthesis and implementation again. Just one point is that here I have increased the frame size to 32 bits. As a result, this signal should also be 32 bits, and this signal is driven by in fact this Axi GPIO, and here in this Axi GPIO I want this guy also to be 32 bits. So I double click here, and in the IP configuration, I increase the width of this guy here to 32 bits. So this 32 bits, so 31 to 0, and then the signal goes directly back to our sample generator. I think the design is kind of in a stable state. I save it and I go through the usual steps that we have talked about many times before. So updating the top level HDL, okay, warnings not important. I have talked about these warnings in previous video in lesson 9. And then I go through generate output products, and then I go through run synthesis, and then run implementation and create bit stream. So I will do these steps and I will come back to you. So I just pause the video recording. Okay, now the bit stream is generated. So we have the updated bit stream, and to continue our analysis on the design, I come back and I go into the software development kit environment. So I come and go to the SDK folder, and now I want to run the Xilinx software development kit. Actually, this is the folder that we used to create our software in previous videos of this lesson. And now, in order to run the software development kit, I simply run XSDK. And it asks me about the workspace that I want to use. The address for the workspace is correct. I go ahead. Okay, here we have the workspace, and I have described to you all of these items before in the previous sections of this lesson, so you clearly know what is FSPL and what is hello world and what is inside each one. So this is our program, which is actually we have called hello world.c, and actually is the program which initializes the system, initializes the interrupts, and then it starts DMA transfers. Yes, and I have described all of this program to you previously. But now there are some questions about this code, and one interesting question that I have been asked is that when this function gets executed and actually the DMA transfer gets begin, when this is executed, the next command that will be executed after this subroutine will be this return 0. And after that, what will happen? In fact, how we are sure that after this point the CPU is still in our control, so that whenever the interrupt happened, the DMA interrupt happened here, this interrupt handler is executed. So one idea is, after a start DMA transfer, you enter a kind of infinite loop and you spin in the loop, and whenever the interrupt appears, in fact the interrupt handler will get executed, and you are sure that you are not losing the control flow of the program. Actually, this is practically not needed. I mean, I have finished the main function completely normally. After starting the DMA transfer, I say return 0, and then I finish everything. And this operates correctly because after this code gets compiled, that spin loop, that infinite spin loop, is added automatically to the end of your program. Okay? And how do I see that? How can I analyze, in fact, what is the output of compilation? What is practically the code, the set of opcodes which are being executed on the ARM host of the ZYNQ? So there are plenty of different solutions, but you can disassemble, in fact, the ELF that is created for you. So I have written this code. This code is
compiled, and now I have this ELF file here, and you can convert or disassemble this .elf file very easily. How do I do that? I come here to the SDK folder, and here inside the SDK folder, first I find the ELF file on which I'm working. So I have two ELF files, first one fspl.elf, second one hello world.elf. And for this hello world.elf, I want to obtain the disassembled code. So how do I do that? I use the Xilinx toolchain here, okay? Or better to say, the ARM toolchain here. So the ARM toolchain you have used extensively so far. Where do you use the ARM toolchain? When you compile your code, actually. So for example, let's make a silly change in this code, and now look at what is happening in the console when I save this program. Actually, I have changed something. So automatically your code gets compiled. And how does it get compiled? Using this compiler. And this is actually a cross compiler which is running on your x86 platform and is compiling your code for your ARM platform. Okay, and I use in fact one utility provided with this tool chain to disassemble the ELF which is generated. So here I come ARM Xilinx EABI objdump, and with objdump you can in fact disassemble the ELF. So objdump -d and then the name of the ELF that we have here. So copy, paste, and then the output of in fact the disassembled output I copy to an ASM file, to a file with the .asm extension. So .asm. Here is our command. It gets executed, and now you have the disassembled version of the ELF. This is actually the set of opcodes, the set of operations which will be executed on your ARM host. So I take a look at what is generated here with vim, copy, paste. Let's open the disassembled file. This is your disassembled file. Obviously it has some sections, it has a set of subroutines, and if you really explore through this file, you can completely understand what is happening. But now, in order to kind of finding an answer to our question, what happens here? What happens at this point? This is my question. So in order to find the answer to this question, I do a very simple thing. I search for main. Inside this, I search for main, and let's see how many instances of main do we have. We have the main function here actually, and if you look at the disassembled code, you see a strong correlation between this and the C code we have written here. Actually the function calls are exactly the same. Init platform, then for example a start DMA transfer, and then this is practically return 0. This line is return 0, and then after that this function gets finished. Indeed, this main function is called by another function. So if I continue searching for main, I reach here, start, and start is the one who is calling the main here with a branch and link, if I recall correctly. So the main gets executed, and after the main gets executed, the execution of the real ELF is not finished. There are other set of functions which will be executed after this one, and this is underline libc underline fini array. I don't know what does it do, but the next one is exit. And if I look at exit, if I look at exit, what do I see? I see a bunch of in fact routines, a bunch of operations being done, but at the end of the exit, if I look, I have a branch to this master underline exit. let's try and find underline exit. So here it is underline exit. And what does it do? It branches to itself. And this is the infinite spin loop. And this is the answer to the question. What happens when you reach here? Do I need to put a kind of while loop here which loops infinitely for infinite time? No, you don't need to do that, because practically when you get your code gets compiled, it will contain this. So now, in order to be a little bit more sure about this, and in order to see some more features of this software development kit environment of Xilinx, I want to debug the application. So I want to debug the ELF on the while it is running on the ARM host of the ZYNQ device. So how do I do that? In previous videos, I executed XMD, and if you remember, I used the XMD to load the bit stream to the PL part of the ZYNQ device, and then to load the ELF files also to the ARM host and to execute the ELF files. The point is that using the software development kit environment, you can do all of those tasks. Okay, so for now, I comment out this function, and then I program the FPGA. So here I come to Xilinx tools, program FPGA, and in the program.fpga dialog box, you have an entry is called bitstream, in which you define the location of the bitstream that you have. So where is our bitstream? Practically our bitstream is located inside our Vivado project folder. So maybe I have shown the location of this file to you previously, so in the previous video, so I don't need to show it again. So this is the bit file, and I say program. And when you say program, what is practically happening is that, yeah, my board is off. Let me turn on the board. So I turn on the board and I come here, Xilinx tools, program FPGA, this is correct. I say program. And when I say program, what is happening is that if now I come here, view XMD console, here I have the XMD console. What is happening is that when you say program FPGA, the software development kit environment calls the XMD, and through the XMD it programs the FPGA. So it looks like I'm running XMD, and through XMD I'm programming the FPGA. Basically what I showed you in the previous video and what we are doing here through this graphical user interface, they are completely similar. So this was the first step. At the next step, I want to run FSPL, and after that I want to debug my hello world. So in order to run FSPL, what I need to do, I can use, in fact, this icon that I have here. Before running FSPL, let's run the Picocom application so that we can have also a look at the output of execution of our programs on the ARM host. So here I have Picocom. Okay, this is the Picocom here, and I come back to my software development kit, and I come here. I select the drop down list, I select FSPL, and then FSPL will be executed on your ARM host. And how can I check that? I can come here to my FSPL console and see if it's printing something. As you see, the FSPL is executed. The next step, I want to run this hello world, but I don't want to run the hello world. I want to debug the hello world. So here I come to the debug icon, drop down list, hello world.elf, I select it, and it says, asks me, the previous program is already running. Do you want to, in fact, terminate it? Yes, I want to terminate it. FSBL is executed, it has done its job, so I can stop the CPU and run the new program. So yes. And now the layout of the software development kit environment will change, because practically we are going to debug this application. So here I have the C source code of my application, and here I have its equivalent disassembly. And now here you have the famous buttons that you use for debugging applications: step over, step into, and here you can in fact define breakpoints. So right now, as you see, I have defined a breakpoint here on return 0, because I'm kind of interested to see what's happening here. So I have a breakpoint here. This line is commented out, so I don't need a breakpoint here. I have a breakpoint here on return 0, and what I do, I just run the program. Okay, the program is running. It's not reached the breakpoint yet, and as we can guess, is now here, is executing this get char command. So I should go to my console, and probably in the console I should do something. Yes, I should press a key so that the program execution can continue. Yes, it's because of the get char function. So I press enter, and as you press enter, as you see, something happens in the SDK environment. What happens is that the execution flow reaches this breakpoint and stops. So we are now here, return 0 function, and as I showed you, this return 0 is equivalent to move 0 to R3 register of your ARM CPU. So from here you can in fact step into and see in detail what is going to happen. So let's step into, and what is happening is that here now I come back in fact to the start function. So what is this function that we are right now in? Underline start, as I showed you before, and inside underline start we have executed the main, and now we are going to execute this function, and I'm not really interested to see what is happening here inside this function, so I just step over this and I come here, exit, and I go inside exit. So step into exit, and now I enter exit, and now you can really follow where your program counter, where execution flow of the program goes. So you can continue with in fact step intos or step overs or whatever you like. Anyway, we reach this point that is called underline exit, and this underline exit, what's happening inside is that we have a branch to itself, and this is the spin loop, and practically we will stay here forever, because now in the program that I have indeed, as I showed you, I have commented out the .dma transfer, and since I have commented out this part, when it reaches this point, nothing will happen again, though the interrupt will never happen. And since the interrupt will never happen, in fact the interrupt handler will never get executed, and since the interrupt handler will never get executed, in fact no DMA transfer will practically happen during execution of this program. It's obvious. Okay, so now we have learned how to use the software development kit environment to debug our application and to program the FPGA, and as we noticed, in fact running the things over the XMD console is exactly similar to using this graphical user interface that we have here.